Welcome to Tech Lab by Sid. In this video we are going to discuss about ACID properties in database systems. When we talk about databases and transactions, we often hear the term ACID. But what does ACID mean, and why is it so important? ACID is an acronym that stands for Atomicity, Consistency, Isolation, and Durability. These four properties are critical for ensuring the integrity and reliability of transactions in a database system. Without them, databases could encounter errors, inconsistencies, or even data corruption, especially in scenarios involving system failures or concurrent transactions. Let's dive into each of these properties and see how they contribute to the safe processing of transactions. To understand ACID, it's essential to first understand what a database transaction is. A database transaction refers to a sequence of operations that are executed as a single unit of work. A transaction can involve multiple operations such as reading, updating, inserting, or deleting data. For example, in an online banking system, transferring money from one account to another would involve multiple operations, debiting one account and crediting another. These operations must either complete entirely or not execute at all. This is where ACID comes into play, ensuring the transaction's integrity. Now that we have a basic understanding of what a database transaction is, let's explore the significance of ACID properties. ACID ensures that transactions are processed safely and reliably. Atomicity ensures that a transaction is treated as a single unit, meaning it either fully succeeds or fully fails. Consistency guarantees that the database will always transition from one valid state to another, maintaining all defined integrity rules. Isolation ensures that transactions are executed independently, preventing interference from concurrent operations. Finally, durability guarantees that once a transaction is completed, its effects are permanent, even in case of system failures. Together, these properties make databases robust and reliable. Let's now break down atomicity, the first ACID property. Atomicity is the concept that a transaction must be atomic, meaning that it must be treated as a single, indivisible unit. This means that a transaction either completes entirely or does not happen at all. Imagine you are transferring money from one account to another. The transaction involves two steps: subtracting the money from one account and adding it to another. If any step in the process fails, the entire transaction should fail. This guarantees that the database is not left in a partial or inconsistent state. If something goes wrong midway through the transaction, such as a network failure, the changes made up until that point will be rolled back, ensuring data integrity. Next, we have consistency, the second ACID property. Consistency ensures that every transaction brings the database from one valid state to another. It guarantees that data adheres to all defined integrity constraints, such as unique keys, foreign keys, and other business rules. For example, consider a bank transaction where you are transferring money from account A to account B. The total amount of money in both accounts before and after the transaction must be the same. Consistency ensures that no transaction will violate the rules defined in the database schema and that the database always stays in a consistent and valid state, regardless of how many transactions are being processed. Moving on to isolation, the third property of ACID. Isolation is essential in multi-user environments where several transactions are happening simultaneously. Isolation ensures that the operations of one transaction are not visible to others until it is fully completed. This means that other transactions cannot see or interact with the intermediate state of a transaction while it is still in progress. There are different levels of isolation, ranging from read uncommitted, which allows transactions to see uncommitted data, to serializable, which ensures that transactions are executed one after another, preventing any overlap. The level of isolation chosen depends on the use case, but the goal is to avoid issues like dirty reads, non-repeatable reads, or phantom reads, which could arise from concurrent transactions. Finally, we come to durability, the fourth ACID property. Durability guarantees that once a transaction is committed, its changes are permanent, even in the event of a system crash. In simpler terms, once a transaction is successfully completed, its effects on the database cannot be undone. For instance, in the case of a successful bank transfer, even if there's a power outage immediately after the transaction, the changes made to both accounts will be preserved. The system ensures that any committed transaction is saved to non-volatile storage, meaning it survives crashes, reboots, or other failures. Now that we've covered each individual property, let's take a look at how they work together to ensure database reliability. Atomicity makes sure that a transaction is treated as a single unit of work. If any part of the transaction fails, the entire operation is rolled back, ensuring that the database is not left in a partial state. Consistency ensures that the database remains in a valid state before and after the transaction. Isolation makes sure that multiple transactions can occur concurrently without interfering with each other. Finally, durability ensures that once a transaction is committed, the changes are permanent and survive any system failures. Together, these properties form the backbone of a reliable and safe database system. To illustrate how ACID works in practice, let's consider a real-world example, a bank transfer. Suppose you are transferring money from account A to account B. The transaction consists of two operations, debiting account A and crediting account B. Here's how ACID applies. Atomicity: if either the debit or the credit operation fails, the entire transaction is rolled back. You won't end up with one account debited and the other not credited. Consistency: the total balance across both accounts remains the same before and after the transfer. Isolation: while this transaction is being processed, no other transactions can access the intermediate state, example, the temporary state where account A is debited but account B is not yet credited. Durability: once the transfer is complete, the changes are permanent, even if the system crashes immediately afterward. Both accounts will reflect the updated balances. While ACID properties are crucial for ensuring database integrity, implementing them can come with challenges. For example, enforcing atomicity and consistency can sometimes result in performance trade-offs, especially in highly concurrent systems. Isolation can lead to issues like deadlocks or transaction blocking when multiple transactions are trying to access the same data simultaneously. And durability can require additional system resources, such as frequent writes to disk, to ensure that changes are permanently stored. Additionally, maintaining ACID properties in distributed systems can be complex, as the database is spread across multiple machines. Balancing these factors while ensuring that performance and reliability are not compromised can be a challenge for database administrators and developers. An interesting comparison to ACID is BASE, which stands for basically available, soft state, and eventually consistent. BASE is often associated with NoSQL databases, which prioritize scalability and availability over strict consistency. Unlike ACID, which focuses on strong consistency and reliability, BASE allows for some level of inconsistency, which eventually resolves itself. This model is ideal for systems that need to scale horizontally and handle large volumes of distributed data. While ACID guarantees strong consistency, BASE embraces eventual consistency, offering higher availability and flexibility. Depending on the use case, developers may choose one over the other, depending on whether consistency or availability is more important. Given the differences between ACID and BASE, it's important to understand when to use ACID properties. ACID is ideal for transactional systems where data integrity is paramount. This includes systems like banking, online shopping, and other financial systems where consistency, accuracy, and reliability are critical. However, ACID may not always be necessary in systems that prioritize scalability and availability over strict consistency. In such cases, a BASE model might be more appropriate, especially for large-scale applications that need to handle high volumes of traffic and data. Understanding your system's needs is key to choosing the right approach. Let's recap what we've covered today. ACID properties, atomicity, consistency, isolation, and durability are crucial for ensuring reliable and consistent database transactions. Atomicity guarantees that a transaction is treated as a single unit. Consistency ensures that the database remains in a valid state. Isolation keeps transactions independent from each other, and durability ensures that once a transaction is committed, its effects are permanent. While these properties are essential for most transactional systems, alternative models like BASE are used when scalability and availability are prioritized. Choosing the right model depends on your system's requirements. Thanks for watching the video. Be sure to explore our channel for more content like this.